Hello everyone. In this video we are going to learn how to perform particle tracking analysis using the MODPATH code. MODPATH is a companion program to MODFlow. Essentially it takes your MODFlow solution and you provide a set of starting locations for what we call particles. These are hypothetical particles that we place in our aquifer at desired locations, and then based on the solution of heads and the flow rates implicit defined by those heads and the hydraulic conductivity and Darcy's law, it tracks those particles either forward or backward in time. And the lines formed by the trajectory of these particles are called path lines. And these path lines are incredibly useful in helping us understand the behavior of our aquifer. It helps us answer really fundamental questions such as how long does it take for groundwater to get from point A to point B in our aquifer, which is often one of the main reasons you develop a groundwater model. And it also allows us to delineate capture zones for wells, which I'll show you some examples. And so in a way it's a post-processing tool for MODFlow in that you generate your MODFlow solution, and then particle tracking allows you to analyze and interpret the results of your model. It was developed by the United States Geologic Survey, and it's fully embedded inside GMS. It's very easy to generate particles and set up a particle tracking analysis. In some cases you can do it in seconds, and it runs very quickly in most cases, and so it's a really nice part of our overall groundwater modeling tool set. So here are some examples of path lines generated by MODPATH. The example on the left, we have this particular use case. There's a hypothetical planned location for a landfill, and if we wanted to determine if that landfill were to leak, where would the leachate go and how long would it take to get to its destination? And so in this particular case, the path lines showed a trajectory of going from the landfill down to a river just south of the landfill. Now notice that these lines are in general perpendicular to your contour lines of your computed head. That's because groundwater flows in the direction of the maximum downward gradient, which, unless you have anisotropy, that's going to be perpendicular to your contour lines of head. And not only that, but if you were in the GMS interface, if you were to click on each of these path lines, it would display for you the actual travel time in days, if that were your time unit. And this is what we call, on the left, we're doing a forward tracking analysis, and we start the particles at the water table surface at the locations shown by the black dots, and we track them forward in time. And on the right hand side, this is what we call a capture zone analysis. In this case, we've generated a circular ring of particles around the location of the well. If you were to zoom in on this figure inside GMS, you'd see a little ring around the well. And then we track the particles backward in time. What that means is, instead of going in the direction of maximum downward gradient, we go uphill in the direction of maximum upward gradient. So we are still going perpendicular to the contours, but we're going in the other direction. Now, why would you do that? The water itself does not flow backwards. The point of that is when you generate this kind of plot, we sometimes call this a spider plot because of these, it looks like a bunch of spider legs coming out from the body of a spider. Basically, this cluster of lines generates what is called the capture zone for the well, meaning that if any contaminant were to be introduced to the aquifer within the location of that capture zone, it could potentially be taken into that well. And so a really common type of analysis for municipal wells is to do they call it a wellhead protection study or a capture zone analysis to determine what region within a basin or an aquifer could potentially be captured by the well. And sometimes you're prohibited from doing certain activities, certain types of industry, or certain types of fertilizers and so forth within the capture zone of a critical well. And so that's just one example of how this works. And when you're doing capture zones, there can also be a time component. If you look on the left, this is the global capture zone for this well, meaning those particles started the well and they went backward until they intersected the water table surface. So that is the complete capture zone, regardless of the travel time. However, sometimes on a capture zone, it would take many, many years to get to the fringe, to the edge of the capture zone. And so sometimes it's useful to delineate time-based capture zones. So on the right, you'll see a series of capture zones that were generated by putting a limit on how long the particles could travel backwards. So if you do a maximum travel time of 1,000 days, you get that smaller zone, and then 2,000 days and 3,000 days. And so when you generate a capture zone, you can choose to do either the complete capture zone or a capture zone associated with a very specific travel time. And depending on your application, that could be a critical thing. So that, for example, that middle capture zone there, anything that falls in between the 2,000 day and the 1,000 day would have a travel time of 1,000 to 2,000 days and so forth. So it's fairly intuitive how this works, but how do we go about setting it up? So when using MODPATH inside GMS is very easy. First of all, you run ModFlow. Make sure you have defined porosities if the travel time is important, which it typically is. And GMS provides a default value of porosity of 0.3, but that's just a guess. You should consider that and decide if you need to change it. And then you generate a set of particles. And once you do that, the path lines and your capture zones are automatically computed and updated. And after you generate the particles and set it up, each time you make a change to your ModFlow model and save it and run it, when you read it back in, not only will the head contours be updated, but in general the path lines are updated as well. Now, if you have a really big transient model, I believe there's an option in GMS to only calculate the path lines when you tell it to, but the default is to have it automatically calculated each time you read in a new solution. So once you set it up, it's just like in a way it's like a display option. So to generate your particles, there are a couple of primary ways to do that. One method is in the ModPath menu, there's a Generate Particles at Wells command. And what this does is it just goes through, and for all of the wells in your model, it will generate a circular ring of particles around the center of the cell as shown in that diagram on the right. And the default is 20 particles, but you can change that. If you have both injection and extraction wells, you can indicate which type of wells. Sometimes we have groundwater remediation systems that have both injection and extraction wells. And tracking particles forward in time from an injection well can be a really useful way to look at the region of your aquifer that's being flushed by this injection-extraction well combination. But usually we're using extraction wells, meaning we're pumping water out of the aquifer, and we want to travel backward in time. And at the bottom, when I generated this dialog on the left to do the screen capture, I didn't have any wells selected, so it's just defaulting to all of my wells in the model. But let's say you have a few hundred wells and you just want to do particle tracking for a few of them. You just need to select the wells, and you select the cells containing the wells of interest, and then that bottom option will allow you to only generate particles at the selected cells. And so that way you can confine it to just a subset of your overall wells. Another option is to select a set of cells, and then there is a generate particles at selected cells command. And when that comes up, for example, using the case on the left, this is the landfill case I was talking about. When I generated this screenshot, I selected a set of cells corresponding to the location of this landfill. And that's that rectangular set of cells on the left. And then when you bring this up, there are two main things. There's a slider that controls how many particles to generate per cell, and then where it says distribute particles, that tells you how the particles are distributed on or within the cell. So one of the options is on water table surface. So what this does is it assumes that you are on the top layer, and it takes the particles, and there's an option in the input to MODPATH to say this particle is going to start out at the elevation corresponding to the water level at whatever that XY location of that particle is. And so that if you're doing forward tracking to see where any kind of contaminant leaked into the water would go over time, this is the option you would generally use. And that slider, if you pull the slider all the way to the left, it would be one particle per cell, and you'd have one particle right in the center of the cell. But as you slide it to the right, whatever number of particles are generated or in that list would be evenly distributed along the face. So in this case, it would be 6 particles per cell, uniformly distributed on the face of the cell, as shown by the diagram there. And so you can have multiple particles per cell if you want. So you can have any kind of density you want. And there's also, if you click on the bottom there, there's a more options command, and I don't believe I have a diagram of that, but you can play with that. You can actually control very specifically how the particles are distributed throughout the cell. But this gives you some defaults. The next one in the middle is on cell faces, and what this does is it gives you a ring of particles on the little square defined by the middle of the cell vertically, and then it just distributes the cells around the particles around the perimeter of the cell on the face. And then the other option is within the cell. This just puts particles uniformly distributed throughout, spatially throughout the cube defined by the cell in X, Y, and Z. And sometimes that's useful as well. So yeah, a lot of different options. And another one that I don't have shown here is, in some cases, you can even import a file with a set of particle starting locations. I used to have a slide on that, but I've been doing this for a few decades and I don't recall ever using it, so I took it out. Obviously, 99% of the time, these options that I've shown you give you everything you need to generate the particles where you need them. Another thing is when you generate particles, they are organized into particle sets. In the 3D grid section of the Project Explorer, there's a folder for particle sets. You can right-click on that and generate a new particle set, or if you start out without a particle set and you do either of those two commands I just showed you, generate particles at selected cells, or generate particles at wells, it would automatically generate a new particle set for you. But you can manually create new particle sets, and one of those is active at any given time. And if you want to add new particles to a set, you just need to make sure it's active and then use either of those commands I showed you, and then they would be added to the existing set. For each particle set, you can give it a name. You can also define if it's going to be going forward or backward in time. And then under the track column, there are two basic options. You can three options. You can go, if you're going backward in time, you can go to the beginning, meaning go as far backward as you can go until it reaches a boundary or the water table surface. And to the end means just track it as far as it will go until it exits the model or reaches a well or something. Or if you do the duration, then that last column is undimmed and you can give it a time value. So in this case, that Wells 1000 particle set would be tracking backward in time for a duration of 1000 days. And so you have very strong control over these tracking options. For particle sets, there are a number of display options. You can have different symbols for the starting and ending locations. You can change the color of your path lines and the thickness. You can put little arrows on top of your path lines to kind of show the direction they're going. And then there's this zone code thing. I'll talk about this a little later on, but your particles can be associated with different zones in your model, and you can color code them based on their zone, and that is really nice as well. And then this section here on the lower left is display options for capture zones. And so it will automatically generate capture zones if you're delineating, if you're doing backward tracking from wells, and you can fill those capture zones. Some of the images I showed you a few minutes ago were generated using this particular technique. And this is something that is best learned through practice. These are really basic options, and so if you just play around with it for a minute, you can figure it out pretty easily. This is really straightforward when you're doing a steady state model. When you're doing a transient model, it gets a little more complicated because we're going to talk about this more in a subsequent video, but when you're doing a transient model, your simulation time is subdivided into stress periods, and then each stress period is subdivided into one or more time steps. And so your simulation time starts at the left and goes forward, but sometimes what you want to do is do backward tracking at some point in time in the middle of a simulation. So maybe 3 years into the simulation, I want to generate some particles and then run them backward in time to do a capture zone analysis, for example. Or maybe you want to go forward in time. So if you're doing a transient analysis, you have an option to set up a reference time, and then just your forward tracking goes relative to that particular time. Also, I mentioned porosity. As we learned earlier in one of our earlier videos, in order to determine seepage velocity, or in order to analyze travel time using Darcy's law, we need to get seepage velocity, and so we need to divide our Darcy velocity Ki by the porosity, and the seepage velocity is the distance divided by time. And so implicitly inside MODPATH, it's calculating the travel time along these path lines, but the only way it can do that is if it has porosity. And I should have put the NE subscript on here to mean effective porosity, but that should be understood, that we always use effective porosity when we're dealing with seepage velocity. And so the porosities are stored in a grid. There's one porosity value per cell, the same way we store like hydraulic conductivity. And you can define these by zones in the map module and then have them mapped over to the corresponding cells. You can then edit them in the spreadsheet dialog the same way you do hydraulic conductivity, or you can select cells and then bring up the 3D grid cell properties dialog, either by right-clicking on the cell and doing porosity, or double-clicking on the cells, and then you can manually edit the porosity value assigned to the selected cells. So that's a pretty straightforward thing to do. Earlier I mentioned zone codes. Each of the cells in your grid has a zone code. The default zone code is 1, but you can change it so that you have zone 1, zone 2, zone 3, and these are just integers. It's a lot like the I-bound array. And the reason that you may want to do that is because if we go back to the display options right here, you'll notice that we can delineate capture zones by zone code or this path lines. Right now it says default color, but if you pull that menu down, another option is by zone code. And you can, if you have multiple zones in your model, in this case I only had 1, but if let's say I had 3 zones defined by these integers, I would have 3 different entries here, and I could assign a color to each of those. And then I can color my path lines based on either the zone code of where they start or where they end. So looking at this example here, we have, in this case, we have our landfill case, and we have a rectangular section where the particles begin, and we track them forward in time. But in this case, some of the particles go to the river, and some of the particles go to this well. So if we select that cell containing the well and give it a zone code that's different from these cells at the river, we can then delineate the path lines. We can have the color dependent of the ending zone code, so where the particles end. You can either do it where they begin or end. In this case, we're doing it where they end, and that clearly delineates which of these lines are going to the well and which are going to the river. And so again, the zone codes, you can define them by polygons in the map module or selecting cells. Typically we select the cells, and using the properties dialog we edit that zone code. Here's another example. This is a 3D rotated view of a set of wells. It's also possible to generate this kind of display for wells. So these shapes here represent the screens on a well, and in each of those there's a ring of particles around the wells. Let's look on the upper right first. And in this case, in the upper right, the path lines are colored based on the zone code of where they start. And they start at the wells and they go backwards. So you can see these are purple, these are blue, and then this kind of intersects sometimes you have a capture zone within a capture zone, so these 2 colors would help you understand that. And then this lower set here, these 3 here, in this case it's coloring the particles, or excuse me, the path lines based on the zone that they're passing through. So you'll see that these path lines change color as they move through the grid, and that's because we've defined different zone codes within the path of these path lines and are coloring them based on that. So there's a lot of variety here in what you can do. It's really limited just by your imagination, I think. All right, back to the issue of capture zones. Notice these beautiful time-dependent capture zones over on the right. In this case, I mentioned that we can look at the set of lines that are tracked, and the capture zone is defined by the overall area defined by those lines. But actually, GMS gives you a way of looking at that set of lines and actually creating a polygon. which you can display, and there's even a way to save that to a shapefile so you can export it to other applications. So how does that work? Well, it takes these path lines have a series of points along the path line defining the trajectory. And so what it does, it takes each of those points and it creates what we call a vertex or an individual point, and then it triangulates those using what's called a Delaunay triangulation. And then any long, thin triangles on the perimeter of the triangulation are deleted, and the outer boundary of the resulting set of polygons becomes the capture zone. So this next figure will illustrate that a little more closely. Let's look at the one on the right first. And so imagine each of these blue lines as having a large number of little points. And basically we triangulate this whole set of points, and then we look at what's called the convex hull of that triangulation. Now, we're not displaying the triangles here. This is all done implicitly. But the outer boundary of those triangles defines our capture zone. Okay? And that's basically the little trick that GMS does internally to give you a capture zone. That way you can display this boundary around the capture zone, and then you can color fill inside the capture zone. And again, I believe there's a way to export that as a polygon, as a shapefile as well. Now, there's something called the thin triangle ratio that if you look at the GMS documentation, it'll describe that in more detail. Basically, there are some long, thin triangles on the perimeter of this triangulation, and if the ratio of the two short sides divided by the long side is larger than the ratio shown, it will delete them. And just keep in, and it doesn't matter if you fully understand that, but basically this is almost like providing a vacuum. If you think of this perimeter around these points as like a balloon or something, this thin triangle ratio will kind of suck the air out of that balloon and pull it in. So, why would you ever want to do that? Clearly, the one on the for a nice, well-defined capture zone like this, the one on the right is probably what you'd want to use. But let me show you another one. In this case, there's some curvature to it, and so along this section, right? Let me show you. Start on the right. When you triangulate this, those triangles are going to span these spaces here. So there's a little bit of a jog at the end here. I don't know why, of these path lines as it gets up to this edge, and this concave zone here gets spanned by the triangles. And so in this case, if you scale back that thin triangle ratio, you just try some numbers and experiment with it. But in this case, if you scale it back to 0.96, it basically, like I said, it's like sucking the air out of a balloon. It pulls it around these path lines, and you get this shape shown on the left, which for this particular case I would argue is the more accurate looking capture zone. So again, that's just a display option. It's something you can play with if you want it to automatically delineate those. You can always export those path lines and just go in and click out a polygon yourself. You could even do that in the map module of GMS. You could make a generic coverage, polygon coverage, and just go in with the arc and polygon tools that you're already familiar with, and interactively sketch your capture zone on top of your path lines, and then export that to a shapefile, and that works just as well and gives you ultimate control over it. So there you have it. That's a quick overview of particle tracking with MODPATH. Again, it's very easy to set up and use, and I hope you find it useful as you analyze your groundwater models.